Hi, welcome to another Druid Summit 2022 session. This session is titled Load Drop Kill. It's about the life cycle of a segment in a Druid cluster. My name is Sergio Farragut. I'm a Senior Developer Advocate here at Imply. And today we're talking about the retention rule. First, we'll talk about the multiple historical tiers. So this is the idea of grouping sets of servers that are running the historical process into tiers and using them in different ways for better cost efficiency of your overall workload. So we'll talk about that. We'll talk about segment retention rules that define how segments are instantiated in each of the historical tiers and how they migrate from tier to tier based on those rules. And we'll discuss the lifecycle of a segment from ingestion through multiple tiers given a set of rules. And finally, we'll touch on the new lifecycle of a segment, so the changes in behavior of this process coming up in Druid 25 to make it even better. So let's get started with historicals. So this idea of multiple historical tiers is you're grouping a set of servers that have the same characteristics into a group of nodes that are targeted for a particular kind of workload. Right, so you could have things like a hot tier where it's a set of nodes where they're all i3 4x larges as an example, with 16 vCPUs, 122 gigabytes of RAM, and they use SSDs with a total of 3.8 terabytes of storage in each of these servers. Right, so these are high-powered servers. Then you could have another set of servers, which we're calling cold tier here, that have a lot less power. In this example, we're using D3 2x larges for this, right? Where there's 8 vCPUs for each of these, 64 gigabytes of RAM, and a lot more storage, right? It uses hard disks, which are slower than the SSDs on the other ones, and a lot bigger ones, so there's a lot more storage in these servers. So this renders different combinations, right? There's a higher cost per gigabyte of storage in the hot tiers than there is in the cold tier. There's a higher memory to storage ratio in the hot tiers than there is in the cold tiers. And this means that we'll have more in-memory caching in the hot tiers than we do in the cold tiers, and there's faster I/O in the hot tiers compared to the cold tiers, right? In this example. Now, why would you want to do this? You'll have a lower cost per gigabyte, a lower cost per queries in the cold tier, and you will have the side effects of that, which are slower queries and being able to address less concurrency than you would in the hot tier. With the hot tier, you're getting higher cost per gigabyte of data, but you do get faster queries and you're able to address higher concurrency. So the idea of defining multiple tiers is finding this cost efficiency given your workloads and given the temperature of the data, how much each of those data sets is queried and what the SLAs are on those. So this allows you to fine-tune that across multiple servers. So once you have these tiers defined, the coordinator is the process that manages the segment distribution, right? It will look at all of the segments that have been ingested into deep storage, and it'll apply retention rules to each of them, issuing commands to the historicals in each of the tiers to either load segments into the historicals, unload them from the historicals, perhaps mark them as unused if the segment is no longer needed, and then finally killing segments, which deletes them from both the metadata and the deep storage in the end. So this is the overall what the coordinator job is doing. The way it does it, it reads from the metadata all of the segments that have been ingested. So it recognizes all of the segments that are marked as used and ingested into deep storage, and then figures out which rules need to be applied to each of those segments. If a segment belongs to a specific all segments belong to a specific data source, but if that data source has specific retention rules defined for it, those are applied first. If it doesn't, it will only apply the cluster default rules. Now, you could have both, where you have a set of rules that are data source specific, and those are evaluated in order first. And if none of those match, then it'll fall into the cluster default rules and see if any of those rules match for a given segment, and then apply those accordingly. But now let's talk about exactly how to configure these rules. One of the ways of configuring retention rules is to go to the Druid console into the data sources view, where in each row you'll find a data source, and each row contains this column called retention. In the value of that column, you'll see what the current retention rules, which retention rules are currently being applied. In this example, we see that it's using the cluster default rules, which means that no specific rules have been defined for that data source. But you can click on that pencil icon to edit the rules and specify rules for that particular data source. So when you do that, you get this pop-up window. In this example, we're editing the retention rules for a data source called taxi trips month. So you add rules, you can add as many rules as you want, and the order of these rules is important. So the first rule that matches a given segment will be applied. Normally, you'll see that the data source retention rules have a final rule at the end using a forever rule. Usually it's a drop forever rule, such that any segments that are evaluated by these rules, if they don't match any of the data source specific rules, they will not fall into the cluster default rules, right? Now, if you don't include a forever rule as the last rule in your set of retention rules for a particular data source, then it will normally fall into the cluster defaults and follow whatever those rules are and see if any of those rules match the segment. You can edit the cluster defaults there at the bottom where it says cluster defaults, the edit link there. You can click on that, and a similar window will pop up, but you'll be editing the cluster defaults. You can also change retention rules using an API. The API, you can use a POST request to the endpoint at Druid Coordinator v1 rules, followed by the data source name for which you want to set the rules. If instead of the data source name you use _default, you'll be setting the rules for the cluster defaults as a whole. The payload is an array of JSON objects. Each JSON object is a load rule or load or drop rule that specifies which tiers and how many replicants for each tier you want, if that rule matches, and what kind of rule is, what period it applies for. But let's talk about rules and what kinds of rules exist. So first of all, we need to think about rules based on what time frame they cover, right? So you have load, drop, and broadcast rules that can be either forever, by period, before by period, that only applies for drop, or by interval. So forever rules, well, first of all, what this does is it looks at the segment's time interval, right? Each segment covers a particular time frame. It has a start timestamp and an end timestamp, but so it has this time frame that it needs to compare against a rule. In the case of a forever rule, all segments will match regardless of their time interval, right? So forever means always match. By period, you specify a time period, right? You use an ISO representation of time, like P1D for 1 day, P1M for 1 month, P5D for 5 days, and so forth. But that's measured back from now. So you'll have 5 days back from today if you have a P5D period where segments will match. In that particular kind of rule, you can use an include future flag. So if that's turned on, that means any segments that fit within that period, the past 5 days or whatever that period may be, or falls into the future. If you're loading timestamps that are in the future, those will match as well. And now a drop before by period, this only exists for drop rules. But before by period is the exact opposite of the by period, right? So you still define the same period, say 5 days, only segments that are before that period, so that are before the start of those 5 days, will match this kind of rule. They only exist for drop, right? So this is a way of dropping segments that are beyond a certain time frame. And finally, the by-interval rule, which specifies static intervals. So the by-interval has a start timestamp and an end timestamp. So segments that overlap with their start and end with that interval will match that kind of rule. Let's say what we can do with each of these rules. We've talked about the time frame of the rules, and that's how they're used to match or not match. But then there's the action of the rules, right? So there's the load rules. So if a particular segment matches the time frame of the rule, it will then apply the tiered replicants result to that, right? So in this case, we're saying load by period with a period of P2M, so 2 months. So all of these segments that in this example are 1 week long will match as long as they still overlap with those last 2 months, and they will get 2 replicas in the hot tier for each of those segments. So that'll be the result of this rule. If they're past those 2 months, then we'll check the next rule in the list. Drop rules will, whenever they match, will mark the segments as unused. What this means is that if the segments are present in any historical at this point, they will get unloaded from the historicals. And whenever a kill task runs, and we'll talk about that separately in a moment, but whenever the kill task runs, it will look at any segments that are marked as unused and remove them from the metadata and from deep storage as well. And finally, broadcast rules. Broadcast rules are less common. They allow you to, again, match based on a time, on whatever the time frame is for the rule. But segments that match this rule will get replicated to all historicals. So you get a broadcast, right? All historicals, all brokers, and all indexers. This is typically used for very small data sources that you want everywhere. You may be using them for joins, and therefore having them in the brokers is useful as well. But anyway, they're copied everywhere and used everywhere for broadcast kind of joins. So let's look a little more detail into what the coordinator is actually doing and what the overall cluster is doing through the processing of retention rules. So if we start from the left here, the first thing that happens is that the coordinator runs on a period, right, on a cycle. It runs every minute, this operation every minute. By default, you can change that period by changing the Druid Coordinator period parameter. But it starts by reading the metadata, right? It reads all of the segments from the metadata database and, all the segment metadata from the segment metadata database. And it reads the retention rules as well. So it gets the latest segments that have been ingested and are in used state, and it gets all the retention rules. It also gets the current state of the cluster from the historicals themselves. So whenever historicals load a segment into their local cache, they will announce that they have completed that operation, and therefore that segment is available in that historical from that point on. And so they announce this. They usually announce this either through Zookeeper, that's a default, or they can announce it through HTTP to tell the coordinator and tell the brokers what data they have. So in this cycle, for each segment, we'll see that the coordinator will find the rule that matches. So it'll figure out which rule matches that particular segment. And with that, it'll calculate the desired state, right? So how many replicas does it need for each tier? It'll also look at the current state for that segment, and also in terms of how many replicas currently exist in each tier across all historicals in the tier. And based on the differences between the desired state and the current state, it'll issue load and drop commands to each of the historicals by adding them to each historical's load queue. Each historical's load queue is the list of commands that it needs to execute, whether it's a load a segment or drop a segment, and each historical will independently process those commands. The coordinator also does segment balancing by tier within this process. And the way it does that is it looks at the current state of the historicals, and it picks based on if storage of the segment cache in each of the historicals is out of balance. It will pick a few segments to move from the historicals that are overloaded or that have more load than others, and select which historicals to move them to. So it'll move segments around between historicals within each tier to keep them in balance. There's a few more parameters that govern this overall process. If you look at the replication throttle limit, that determines the maximum segments to replicate in each cycle. This is different than just loading new segments, right? There's two different activities here. The coordinator prioritizes loading segments that have 0 replicas in the tiers that they should have at least 1 replica in. So it'll do those first. And then it'll look for under replication and pick which segments to replicate, so to issue more commands to other historicals so that it creates replicas of these segments in other historicals. The default is 10, which is rather small. It's good for tiny cluster, but you may need that number to be bigger, 100 or 1,000 in larger clusters in order for this replication to occur quicker. You can also control the max segments to move. So this allows you to control how much of the balancing work is done in each of the coordinator cycles. The default is 5, which is also somewhat small. So as the cluster grows, you may need to increase that parameter as well. You can control the queue depth in the historicals. That's with the max segments in node loading queue parameter, which defaults to 100. It's one setting for all historicals, so that means that you'll get up to 100 commands issued or 100 commands pending in a historical from the coordinator. If any of those load queues are full, the coordinator will stop sending commands to those historicals. You might need to change the depth of that, although 100 is probably a good value to begin with. Now you can control how fast the historicals process those commands by controlling the number of threads that are dedicated to that process. And that's up at the top here, top right, we see the Druid segment cache num loading threads. That's what that parameter does. It defines how many threads each historical is going to use to execute the commands that are coming in through the load queue. Obviously, the more threads you have there, the faster it will be able to get through the commands that it has. So you may need to tune that in some cases to increase the parallelism of that operation, particularly if you're doing like an initial load of a cluster or something of that nature. But normally it defaults to, it has a minimum of 1. There will always be at least 1 thread doing that operation. And it'll default to if it's larger servers that the historical is running on, it'll do number of cores divided by 6, so by default. You can change that setting manually if you want, but the default tends to work pretty well. So finally, I promised we'd talk about the kill task. So this is another operation that the coordinator does on a cycle, right? The period for this is slightly different. It's the Druid Coordinator kill period, and it defaults to once a day. So once a day, the coordinator will run this kill task, and it'll go through all of the segments that are currently marked as unused and remove them both from the metadata and from deep storage. So this frees up deep storage and keeps the metadata clean. So those are the definition of the retention rules and what they can do. Let's do an example, set some retention rules up and see what would happen in the cluster. A common use case is aging of segments through tiers, right? Where we want the newest data in the hot tier, right? In the powerful servers, so that because newest data tends to be queried more and tends to have more stringent SLAs, so you'll want more power behind those. So you create a load rule for, let's say, 1 month of the data, including future, to be loaded into the hot tier. And then we have a second rule that covers a whole year to load these segments into the cold tier. Notice that what this means is that we'll have most recent month of data will only exist in the hot tier, and then 11 months of data beyond that will exist in the cold tier. Once the segments go beyond the year, then they drop into the drop forever rule, and they'll get marked as unused and dropped from the cluster. So given this set of rules, let's see what happens in a cluster. A cluster starts by, a new segment starts by its ingestion, right? So the data is ingested, a new segment is created within the indexers or the middle managers, and at some point it's published into deep storage. When it's published into deep storage, it also appears in the segment metadata as a new published segment. The deep storage copy of this segment becomes the golden copy of that all historicals will use to download when they're instructed to do so. So the coordinator kicks in and it will look at this new segment, and given that it's new data, so that it has recent timestamps, it covers a new time interval, it will fit within the 1 month plus future rule. So 2 copies, because that's what our load rule says, two replicas in the hot tier. So 2 copies will get loaded into 2 different historicals in the hot tier. The data sits there for a month, it gets queried throughout that time, and then when the month passes, the segment now matches the 1 year rule. So now it says, I want 2 copies in the cold tier. So the coordinator will issue the load commands to historicals in the cold tier, have those segments be loaded there, and then once that occurs, the coordinator will recognize that the other copies are over-replicated, so that segment is over-replicated, and there should be none in the hot tier, so it drops them from the hot tier. And finally, when the year passes, you'll see that the segments that are in the cold tier will match the drop rule. They'll get marked as unused and will get dropped from the cold tier at that point. Sometime later, within the day or so, when the kill task runs, the kill task will recognize this segment as no longer being used because it's already been marked as unused, and it'll remove it from deep storage and from the metadata. Now, let's talk about a slightly more complex situation. Let's say that we have those same set of rules, right? So their first load rule is 1 month with 2 replicas in the hot tier. Let's say the hot tier is bigger, right? And we have 6 historicals at this point, and they're spread across different availability zones because this is deployed on EKS. So the appropriate way of doing that is across multiple availability zones. So a failure in an availability zone doesn't wipe out all your historicals, right? So you'd want to configure it this way. Now, if our load rule and our hot tier are configured such that all of these 6 historicals belong to the hot tier, you could fall into the situation where the coordinator picked historicals 1 and 2 for those 2 replicas. And so they're in availability zone 1, and you could have a failure in the whole availability zone. So you could run into this situation where you no longer have any copies of that segment when this occurs. Now, the coordinator will kick in. It'll recognize that the historicals are gone, and it will, at some later point, about a minute later, will issue instructions to other historicals to load them. Now, the problem is that between those 2 things, right, during that time where the historical has not yet created a new copy into the remaining, the coordinator hasn't asked for a new copy within the remaining historicals, the broker could see this as data that's not there, right? The broker relies on the data that the historicals are reporting that they have, and because we lost that availability zone, those historicals don't exist anymore. So from the broker's perspective, those 2 segments don't exist for a little while. So it could return query results during that time frame that are incomplete, that don't have the data for that particular segment. So there is a way to alleviate this issue using load rules. You can configure the more tiers, right? Configure, let's say we have, again, hot and cold, but because we have these availability zones, or they could be racks, right? They could be servers on a rack where the whole rack could lose power or something, and therefore you'd want to treat them as availability zones. You could configure these multiple servers within each availability zone and create rules that push replicas, at least 1 replica, to each of the availability zones. So in this new load rule, we have still a period of 1 month for the hot data, but we want 1 replica in each of the hot AZ1, hot AZ2, and hot AZ3 tiers, which guarantees that we have at least 1 copy of the segment in each of the availability zones, such that if an availability zone fails, we still have another 2 copies, right? So this certain guarantees that we have copies available even in the failure of availability zones. In this kind of configuration, if you're going to have hot and cold, just realize that minimum configuration, if you're using 3 availability zones, would mean 6 historical clusters, right? 1 historical cluster in each of the availability zones. So this is sort of the minimum configuration to achieve that level of availability. So we've talked about the happy path and the life cycle of a segment and how it moves, and even some failure scenarios and how to use retention rules to alleviate that. Now let's talk a little bit about what's changing between Druid 24 and Druid 25. So in order to illustrate this, let's talk about Druid 24 first. Using sort of the same set of rules here, but I've increased it to 4 replicas to sort of make a point. So let's walk through this, right? We get the segment ingested, it's in deep storage, it's new data, so it's going to get 4 replicas in the hot tier. So at this point, everything's good. We asked for 4 replicas, and we have 4 replicas. Now, when a month passes and the next rule kicks in, it's going to load 4 replicas into the cold tier, and it's going to load those 4 replicas before it removes any of the over-replicated ones in the hot tier. So this, during some period of time, we now have 8 copies of this segment rather than just 4, right? At this point, the load rules are such that the segment is older than a month, and what we want is only 4 copies of the segment, and we want them in the cold tier, right? And for some period of time, we have 8 copies of the segment, so we're sort of wasting space by doing it this way, at least for some time. So what Druid 20, so the over-replicated will remove those, but it'll only remove those after the cold tier has been fully loaded. With Druid 25, we're changing that behavior. So we'll still see that the new segment is loaded for a month, and it gets 4 copies in the hot tier. So nothing changes there so far. But as soon as the segment is older than a month and we need to start migrating the segment, the way it'll work now is it'll load 1. And then the over-replication process will compare total replicas, right? So in this case, now we have 5 replicas total, and the desired number of replicas is only 4 in the cold tier, but we have 5 in the cluster as a whole. So it'll prioritize unloading 1 of the over-replicated segments to bring it down to 4 before it loads the next one. And then it'll load the next one, and again it'll reach 5 so that it's more than 4, so it'll remove 1 based on over-replication, and as it loads each one of these, it evaluates that, right? It evaluates total replication against across tiers in order to prioritize removing the segments that are over-replicated. And that'll make a much more efficient use of the space throughout the segment migration process. So it's an interesting improvement that's coming in Druid 25. So summarizing, we've talked about historicals being grouped into tiers. We've talked about retention rules and how they can be defined for the whole cluster or for individual data sources, and how you can set rules to control the life cycle of each segment throughout the tiers in a cluster. And finally, we touched on Druid 25 and how it's improving minimizing the overall space utilization during segment migrations. So with that, I'll say thank you and remind you to star the repo, to go to learn.imply.io to get some free courses and certifications on using Druid. These are hands-on courses, so take advantage of that. And finally, point you at the druidforum.org, where the community members publish articles and do Q&A for each other, and all participate there for the Apache Druid community. Thank you.